So how does fusion work? The concept itself is fairly straightforward. Two high-energy nuclei of different atoms collide, and by overcoming the nuclear force, the two nuclei combine, releasing massive amounts of energy. If their product has lower binding energy than the reactants, then the energy in the system has a net increase. This energy can then be captured to do useful work such as producing electricity. Fusion.
There are three ways to transfer this energy: conduction, convection, and radiation. Conductive heat transfer is what happens in this picture. When heat is transferred along the handle of the pot, this heat is transferred between atoms in contact with each other. In a solid, molecules transfer vibrational energy physically to their bonded neighbors. Imagine linking arms with everyone in the class, so you're trapped in a solid form, and then try to transfer energy just by bouncing in place. Conduction also happens in liquids and gases. In these cases, heat or kinetic energy is transferred during collisions. Convective heat transfer is a much more efficient method of heat transfer for gases and liquids. During convection, millions of molecules of gas or liquid transport heat quickly by diffusion or currents. For example, in this image you can see that at the bottom of the pot, heat is conducted by the hot surface to the water at that hot surface. That heat makes that water expand and become less dense. That water then rises to the top of the pot, displacing the colder, denser water at the surface, which then sinks to the bottom and is heated by the conductive pot. Through this process, the heat is rapidly convected through the entire fluid in a continuous cycle. During radiation heat transfer, electromagnetic waves are released from a hot source and spread outwards through space in all directions. When those waves collide with other objects, they excite the molecules in those objects and raise their temperature. Heat is radiated from all objects with a temperature that
systems. The tank sits above the collectors. Colder water sinks into the collectors, whilst warmer water rises unassisted from the collectors into the tank. The tank may sit on the roof with the collector, a close coupled system, or within the roof cavity above the collector, a gravity feed system. With these systems, the roof support structures must be strong enough to handle weights of up to 800 kilograms. Active systems use a small pump to move water between the collectors and the tank. The location of the tank can be within the roof or on the ground.
Next up, we have insulators. Insulators are the exact opposite of conductors. They are poor conductors of thermal energy. They actually block thermal energy. They're kind of like a wall for thermal energy, which is kind of nice because we don't always want thermal energy to leave. We want to keep it and we want to use it. And so in the case of staying warm in the winter, you wear a jacket, which is made out of nice fluffy feathers, sometimes, or just some sort of fabric or whatever. But that fabric has a lot of air in it. It's very fluffy. Air is a poor conductor. It's a good insulator. And so that's why we wear jackets, to keep the heat inside of our body.
Scientists have long known that the presence of an atmosphere keeps the surface of the planet warmer than it would be without an atmosphere. In fact, without an atmosphere, the surface of the Earth would be about 30 degrees Celsius cooler than it is now. In order to understand why, we need to consider the surface of the Earth and its atmosphere separately. Because there is a radiative equilibrium, we know that the planet emits enough long-wave radiation into space to equal the solar radiation absorbed by it. However, most of the long-wave radiation that is emitted by the planet into space is emitted by the atmosphere rather than the surface of the Earth beneath it. Although the surface of the Earth does emit long-wave radiation, only about 10% of this radiation passes through the atmosphere and escapes into space. The rest is absorbed by clouds and by greenhouse gases in the atmosphere.
and how do we perceive them? Well, we have, for example, the violet light, which is about between 380 up to about 450 nanometers. I mentioned in the previous video, and 1 nanometer is equal to 10 to the power of -9, 1/1000th of a meter. Okay, and then we have the blue. Okay, so from here to about there we have blue, and blue is at from about 450 to about 490. Okay, I did that a bit far. Okay, 450, let's put it there. 450 to about 490, that is blue. Then after blue we get green. Okay, and green goes up to about here. From about 490 we go to about 570. Okay, so to about 570, that would be the green portion of the visible light, and then up to about there we have, that's about 590. We have yellow. Okay, and then we have, after yellow we have orange. Okay, and orange goes to about 620 nanometers, and then up to about 750 nanometers. Okay, we have red. Okay, so here we have red, orange, yellow. Okay, after yellow we have green. After green we have blue. Okay, and after blue we have violet. Okay, now the one that I did not mention, and that's actually in here, is indigo. Okay, so there's an indigo color as well, and with that in mind you can almost remember it with, and this is just a way of remembering in which order these colors come. Roy G. Biv, a dude with a name, his name is Roy, middle name is whatever G stands for, and is
with reflection. If we were to look at this leaf, what color of light is being reflected from the surface of the leaf? Well, it's green. Since it occurs as green, we're getting a reflection of that green light. So reflection, remember, is a bounce off of the surface. Now what's interesting is on that bounce, if you draw a normal, which is going to be a line that's perpendicular to the surface, as light is reflected, the angle it comes in at, we call that the angle of incidence, is always going to equal the angle of reflection. In other words, this angle right here is going to equal that angle right there. What if it comes straight in? Then there's an angle of 0, and so it's going to bounce straight back. If we're looking at a mountain in the reflection of a lake, that's going to be reflection that's causing it. And so you know the mountain is not down in the lake. And so how did that image get to your eye? Well, the light from the top of the mountain is reflecting at an angle off of the surface of the water, and it's going to your eye. And so it appears as though it's down in the water, even though it's not. Absorption is different. Absorption is when the light hits the surface and is converted into some other form of energy. Generally, it's going to be heat. And so if we were to look at this leaf, for example, what light is being reflected? It's going to be the green light. And so what light is going to be absorbed? It's going to be the red light and the blue light that's being absorbed. And we can even look at an absorption spectrum of the leaf itself. There are two pigments in there, chlorophyll A and B, and what they do is they absorb a lot of that bluish, purplish light. They absorb a lot of the reddish yellow light, but they don't absorb a lot in the green. And that's because the green is reflected back to us. Now what's neat is a leaf can actually make use of that energy to do photosynthesis. Now light can also